Okay, yeah, welcome. I'm going to introduce, under the title Econometric and Simulation Modeling of Agricultural Systems for Economic Policy Analysis, a little bit what we are doing in our group, but it's sort of targeted to the PhenoRob context here. So first of all, because we're in a disciplinary project, I'm going to say something about what economists do and what perhaps the misunderstanding or common misunderstandings are. Then I will give two types of examples on econometric modeling and simulation modeling, examples that are chosen so that they have some relevance for PhenoRob. Then I talk about CP6, the core project, what we have found or decided already in the first meeting, what direction it's going, what are expected outcomes then of this, and input needed communication across the activities, and then at the end some take-home messages. So what do economists do? We have experience in interdisciplinary projects, and already in the context of the proposal writing, there were some ideas of what we as economists do, and they typically have to do with economists being accountants or doing business administration, so calculating the profitability of PhenoRob technology or something like that. Well, even though there are some types of economists, BWLer or business economists that do that, economics is much more than that, and actually I'm coming from an area that deals with other stuff. So economists study the performance and dynamics of the economy as a whole, the macroeconomists, the ones that are always asked when the central bank changes an interest rate or whatever, and the microeconomists dealing with individual economic decision making and how it scales up to a higher level, but also including the processes that coordinate the use of resources and the distribution of goods. So this is sort of the study area that more microeconomists, but not business economists, are doing. And this is sort of the field that we are also in. Let's look at some, well, what do we do? I'm not the economist, obviously, or my group is not a typical economist group, but we do something specific, and we want to look at some examples with relevance to PhenoRob. So one of the activities we do is econometric modeling of farm structural change. Farm structural change is something that comes in many different ways. So quite often the size distribution of farms is studied, or the specialization, the capitalization, the intensity, how it's mechanized, and so on. And if you look at the whole farm population, then the structure of these elements determine the farm structure. And the typical thing you see here over time is, here we have 3 size classes of farms in Germany that's based on census data, where we see that over time, here from 1990 to 2007, we have an increase in the large farm size, a decrease in the small farm size, and the middle sort of relatively stable. So and we ask, what drives such farm structural change? And theory tells us all kinds of elements or determinants that matter here. Technology, the PhenoRob core thing, changes, differences in technology determine farm structural change over time. But that's not all. Also, where we start from, initial farm structures matter. Market conditions on the input side and the output side matter for what happens over time. Natural resources or the biophysical conditions under which different regions operate matter for farm structural change. Socio and demographical factors, the farmer population or the household population, when are they up for generational change, and so on. Policies. The agricultural sector is one of the sectors with the most, or with the strongest impact of policy on its operation. So in these empirical studies, we then try to analyze the relevance and the strength of the impact of different drivers. So as an example, a study what drives changes in number of farms in different size classes in the EU dairy sector. So methodology, in principle, general, is regression analysis, but a special type. a non-stationary Markov chain analysis, and it allows to identify drivers, impacts, different determinants on transition probabilities between size classes. So ultimately, when you do that, you can then simulate and predict how the farm distribution changes with a quantitative model. What do we find here? Unequal farm size distributions induce stronger structural change. When we have structural change, there are farms that grow, farms that get smaller and disappear, and it's that combination, the distribution, that matters how strong in an area farm structural change happens. Technology matters. Differences in technologies across regions change the dynamics of structural change. Off-farm employment opportunities matter. The household is a complex decision-making unit considering farm and off-farm activities, and what the opportunities are off-farm matter for what happens in the farm sector. One of the things that's more recently coming up is the stronger focus on spatial impacts. So in another study we asked, how does the neighborhood change policy impacts on farm survival? In what sense, how much does it matter who is my next neighbor farm and what are his plans for developing his farm? Well, it's a spatial econometric model, a probit model, where we look or try to explain the probabilities of survival. What do we find? The subsidies that are paid by policies, the subsidies for certain production activities, they matter. In general, when they get higher, farm survival increases. The probability when they get lower, it goes down. However, what also matters is what my neighbors get. Because there's competition. If I want to develop my farm, I need land from the people around me, and depending on what their plans are, the competition for the land increases or decreases. So we can show that it's needed to have these spatial interactions considered when we think about farm structural change. And here you see a probability, a distribution of survival probabilities of farms. And if you consider such spatial effects, then it will be shifted here to the right. We simulated for all of Norway, including all farms in Norway, and decrease in subsidies by 10%. And it's a very big difference between considering spatial neighboring effects or not. So last example for econometric type of modeling is one that already leads to my next topic, the estimation of behavioral parameters for simulation or large-scale simulation models. So we need to empirically base our laboratory, our simulation models with parameters. And we have here in the study by Janssen and Heckelei derived a theory-consistent Bayesian approach to estimate the price dependency of supply for 23 crops across 219 EU regions. The special things about this study is, for one, this large scale. It's very rarely done at this level. And the theory consistency in a model that sort of captures the decision-making of the farms having to choose between many crops under their specific conditions, depending on prices of outputs and inputs and so on. So what we get out then are reaction parameters. Reaction parameters, how farmers in a region behave when the price of one crop category goes up, the price of another goes down, and how are they interacting. Because it not only matters what the wheat price is if I decide to grow wheat, but also what the substitutes, the other alternatives are doing. Simulation modeling, large-scale policy impacts. So we have sort of traditionally that already started when I wasn't even a professor here in Bonn, but later further developed as I was here with my colleague Wolfgang Britz. We developed a modeling system, an agriculture sector model, CAPRI, Common Agriculture Policy Regionalized Impact. And that's a model that's already 20 years operational. It is used by the European Commission for the impact assessment of new policy reforms in the agricultural sector. It's not really our model anymore. It's now a model that's developed, further developed, and continuously used in a network of international consortium. So what does this do? It allows to ex ante evaluate impacts of policy options, European agriculture policy, international trade policies on production, income, markets, trade, and the environment from region to global scale. An exemplary application, but not only with the Capri model, but a whole system of models, is on climate change mitigation. And a recent Nature Climate Change article where Capri was involved did a multi-model simulation of global ag and food system, and they found that stringent climate mitigation drives up food prices and food expenditures, so it has a negative impact on food security, and the increase of the population with risk of hunger is going up. So the interesting thing about that, it's more than the direct impact of climate change. So the food security impact of that mitigation driving up cost of agriculture production, and thereby the food prices will actually have a negative impact that's stronger than the climate change itself. Now, there are all kinds of caveats and limitations, maybe we can discuss later, but that's sort of the main message. Then we look at things like connection of greenhouse gas emissions and mitigation technologies and trade. So governance of the agriculture and food system globally. Trade plays a big role. A lot of products are traded across the globe. And this study here by Hemix et al., Food Policy, it's saying that carbon tax, a higher carbon tax, will trigger the adoption of mitigation measures at the farm level. Trade liberalization itself doesn't have much effect on greenhouse gas emissions, but if you combine them, then you observe leakage. This is sort of an economic concept. Leakage means we impose measures here that lead to mitigation, but because it gets more expensive here to produce it, then somebody else in the global community will pick up the production, and the trade patterns change. And if you have a liberalized trading system, then sort of something gets lost in terms of your efforts to increase mitigation. These large-scale models that I just talked about, these are so-called equilibrium models. They look at the transition from one equilibrium to another. They don't look at dynamics. They are typically rather aggregated, have little heterogeneity in there, and they are static. Okay. So agent-based model are an alternative. It's a surging modeling type able to flexibly capture individual behavior, dynamic agent interaction, and with that then emerging phenomena that comes through the interplay of the parts of the system modeled. These agent-based models, they come actually from the social science, sociology, and they were considered by Axelrod, one of the sort of key proponents, as the experimentation laboratory for the social sciences. But in the last decade, they actually moved to the agricultural, economic, and also the interdisciplinary sciences. And now they deal not only with human systems, but also socio-ecological systems. And we also started experimenting with models of this type. As an example here, a study by Rush et al. It's a common pool rangeland socio-ecological system model. So about a rangeland in South Africa, in that case, common pool means it is a pasture around a village and everybody can use it, feed the cattle, the milk cows there. So it's some community, and this model is a combination of a rangeland model capturing the vegetation dynamics, and by this then quantity and quality of food depending on weather. A livestock model that generates the weight, the growth, how many can be sustained on this rangeland, and an agent-based household model that determines what the stocking rate is of, so what's the use of the rangeland, and they are interacting in a dynamic fashion. So one of the nice things and special things about agent-based models that have individual human decision-making and interaction involved, you can, for the first time, model something like social norms, institutions, in an endogenous way. And one of the features here is that it models an institutional norm that sort of restricts the stocking rate on the rangeland because of expectations and structure of the population in that community. Cannot go into details here. So with this type of model, you can then, under certain conditions, calculate outcomes, dynamic outcomes of what happens to the resource, here the rangeland, when does it degrade, under what conditions on the household or biophysical weather side, and so on. But you also get information about the socio component of it, the households. Same model, we can get as an output the multi-scale resilience. That's for a while that was the more was supposed to be the successor of sustainability. Resilience as being a dynamic concept coming out of the ecology, but having been more and more used also in interdisciplinary research as a concept. So here we can measure resilience at the household level, community level, or at the ecological level with certain measures. And then you can get runs across many different runs, and you see how different management patterns of the rangeland change the resilience, the deviation from the resilience downward. So what you see here, for example, just to give you an intuitive feel, a management that is continuous opportunism. That means you do continuous grazing, no rotational grazing, and everybody puts on what is currently for him or her the best choice. And then you see this is a very irresilient system because these measures here go into the negative range. For example, the vegetation degrades under a drought significantly, the basal cover goes down. So these type of models generate enormous amount of output that are very hard to digest or interpret directly. So some of the newer tools that we use, like decision trees, random forest, also allow them to analyze, do sensitivity analysis, and try to understand what part in the model creates these emergent phenomena is so important. So we can ask ourselves, does a more heterogeneous population leads to less or more resilience? Does a bigger share of non-cooperative population members lead to more or less resilience? Things like this, and we can define where are thresholds, where are impacts on the outcome. Another example for such an ABM model is here in Tanzania. It's a model of agricultural intensification pathways in a floodplain, Kilombero floodplain in Tanzania. So the question is, what determines intensification choices at farm and higher levels? We see direct connection to PhenoRob. At some point we will deal here with what determines the technology choices at farm and higher level. Range of intensification options are given, and then a model is constructed. Dynamic model that shows the diffusion, the adoption of such things. So this model has a socio-economic system, a biophysical system. It's a large-scale agent-based model, 45,000 farmers. This is a real big one. One of the problems of ABM modeling, they are so far very localized, and the connection to the global scale has been a challenge and not pursued much, or to market scale. And here we try to let these 45,000 farmers make decisions and interact via markets on the input-output side with each other. And at some point also in terms of their social direct interaction. The pure decision model that determines now what intensification choices are chosen, or if at all, at the farm level, is here in this case sort of a new approach. It's a Bayesian belief network. So it's a complex network that allows to incorporate all kinds of determinants of the choices made at farm level. It's empirically based, survey based. It gives a probabilistic prediction of intensification choices. So we can say for these and these and these conditions, there are certain conditional probabilities to choose a certain intensification option. Can also be validated out of sample, what we did here. Just to give you an idea what is behind just one agent in such a ABM. Okay, this should be enough. I have limited time. This should be enough for the examples from my group. I already saw Heiner looking at his watch. No, but I still have a little bit. So Jan and I, we are responsible for the core project 6 in PhenoRob, and it's about how to design the process of upscaling the innovations to ease technology transfer, as well as compatibility to current crop farming, and to obtain information on how the new technology will change crop farming systems, landscape, and markets. So that's sort of the mission statement of core project 6. Technology adoption impact at farm and landscape scale. We have met in our first meeting, and actually that was very constructive. Maybe it was constructive because we had a limited number of people attending, I don't know. But we already came up with some pretty clear idea on what the research topics are that we want to attack in the first phase. Topic 1, PhenoRob technologies and the agroeconomic attributes. I come back to that in a moment. This idea here, and that will be led by Jan, is really have a larger concept paper where everybody is involved, and yeah, to also serve as sort of a coordination and communication hub for other things to come. We're going to identify determinants of adoption of PhenoRob type technologies. So we will look at empirical modeling, econometric modeling, experimental modeling of adopting these PhenoRob type technologies. A core activity research topic is to develop a virtual laboratory to simulate the technology diffusion across the farm population and the region then. One of the methods we need to be able to really later work at larger scale is when we have a very complex farm model that is taking a lot of time to be run, has a very rich technology specification, and takes a lot of time to come up with a decision. And we need such farm models then run thousands and thousands and thousands of times, or millions of times, in the process of the ABM. Then it can make this virtual laboratory at the regional level impossible. So one of the things, sort of innovations that we want to bring in is combine our activity with machine learning. There will be a joint PhD project, I hope, if it's approved at some point, with the computer science, where we develop a surrogate model of a complex farm model to allow then to speed up the application of the virtual laboratory. And the environmental impact of PhenoRob precursor technologies, because we don't have many observations yet on what we develop, will also give us some insight on what is the potential here also on the sustainability or the environmental part of the sustainability story. So outcome, knowledge on determinants of adoption, and this is not only at farm level. This takes into account interaction with markets. It takes into account the input side, the technology supply, how it is structured, how it's institutionally structured. Do we outsource to service providers? Do we invest on farm into that technology? How is that related to the attributes of technology? What is important or what is more expensive, and so on. So ultimately, that's the core. We want to generate knowledge for a model that allows us to model adoption of these technologies. Another outcome I already said, ML-based, machine learning-based surrogate model of a complex farm model. So we have available, not in our group, but in a group that we collaborate with in a EU project starting in September, a very complex farm model that we try to develop a surrogate model for that can be very good in predicting the outcomes of that model, but will be much faster in actual simulation. And that will give us then ultimately what we need, technological choice, input use, land use, and with that, the environmental consequences when we have understood how it's connected. Another outcome is this agent-based model of the now social, ecological, technical system, or SETS. Yeah? So there's another dimension coming in, the technical system that's more explicitly looked at. And ultimately, we want to combine theory, social network interaction, farm structure, a really spatially explicit representation using as much empirical data that we get to build here a surrogate, or to build a agent-based model, a spatially explicit agent-based model that then uses at the regional level these surrogate farm models. What do we need from others? Well, we need to learn as we go along about the technology. So we need to understand what are the attributes of the technologies developed here in other activities. What are relevant use cases and their perceived innovation compared to current practices? So we can sort of understand where in our modeling we put this in and where will it make potentially bigger changes and change the dynamics, the structure of the system. So we need regular discussions. And what ultimately, when I tried to witness the core project discussions, and so far it's all very interesting, innovative, detailed things that are foreseen, but nobody has any sort of idea right now how we put this together into an overall crop management system that's related to the technology. So I think this is something we need to find structures for to discuss and move on, because that's ultimately determining what's happening at farm level, but also at regional level. Are there feasible production systems, crop management systems, where this all comes together? And having a working robot alone will not be enough. Take-home messages. Most economists are not accountants, and they do really fun stuff, as you hopefully have seen now. Technological change transforms farm structure and land use. And this is what we are interested in, and we want to really dig deep. Human behavior and interaction matter for outcomes of socio-ecological technical systems, and they can be captured by these agent-based models. That will be one of our focus. Surrogate models can be trained via ML, and we already convinced Jürgen Gall that it could be really interesting also from his research point of view, because there are certain aspects they haven't dealt with or that are in the forefront of machine learning algorithms. So we're looking forward to that. And the last thing, we need to get regular input on technological systems that are sort of developed here in other PhenoRob activities, and hopefully we go beyond at some point the seminar series so that we learn what's going on and coordinate. Thanks a lot.
Okay, thank you, Thomas. We have time for a couple of questions. So, please.
Thanks, Thomas. I learned a lot. A question on the spatial scale. If I understood this correctly, mainly your models start on the production unit, so the single farm.
Yep.
Does this mean that if I go in a production unit like Africa, China, where the production units are extremely small, that you also have to adjust your model to this smaller?
Yes. For example, the example I gave from the Kilobero floodplain in Tanzania, these are very small farms, and each single one is represented with the plots associated to this decision-making unit. Yeah.
You mentioned an interesting factor with farms. The enterprises basically do a lot of other businesses, not necessarily or quite indirect to the farm. Certainly a trend in Australia, for example. I think this is a big factor determining farm sizes, units. How do you explore that?
Well, the approach there is, I mean, it really matters typically what the household composition is. So what are the people earning money? Yeah? And a typical agricultural household in Germany also has not only the farmer, but often other household members that have a job somewhere, or they are part-time farmers. And sometimes this determines whether a certain farm survives or not. Yeah? But it's really in developing countries, it's even more important because there the main profitability of the system is not the key issue. There are other aspects, security, food supply, and so on. So here in Germany, the profitability of the farm will say a lot already for the farm operation itself, whether it will survive or not. However, there are still some other aspects that might lead to sudden, random, in some way random disappearance or exit of a farm because they don't find somebody that takes over the farm, yeah, and then the land will be sold to other units and so on. So in these models, we take that into consideration by looking at age, at farm structure, if a successor is available, what are the regional other alternative employment opportunities, yeah, so that determine also then the decision at farm level.
I have one more quick question. I heard some really interesting statistics about Africa in particular, where most of the farming and the use of technologies is actually by women. And women have been largely left out of the technology discussion. Is there any, is this kind of on your radar? Or?
Well, it is definitely on the radar in development when you do research in developing countries where the agricultural activities on farm are done by the women and they make the decisions. Yeah, it's not.
They might not make the decisions, but
well,
they're doing all they're carrying out all the.
That's right. There are all kinds of different types, yeah, of systems. Sometimes they make the decisions. They have separate household budgets and so on, and sometimes the man does everything, or at least to the outside, but then the woman does the work based on that decision. So that needs to be carefully reflected when you sort of target then adoption decisions, yeah, because ultimately it might be the ones using it that determine whether it's successful or not. So in a developing country context, that would be very important. Most models claim to be gender neutral in that sense, but one has to be careful when you do survey-based analysis and you always talk to the household head, whether you really have the right person to talk to. But it's on the agenda of many people. It's not my specialty area, but it's on the agenda of many others doing work.
So I have a question. As far as I understood, you are feeding your models with information from the past. That means you have numbers for input and output during some regression or whatever, or you have experience for some behavior of agents, and this is all inside your model. So what happens if you have some disruptive changes? Mm-hmm. For instance, let's hope that our new technology is some tiny small machines, autonomously intelligent, doing some fancy things on the field. Perhaps it's disruptive. So how can you handle that? Yeah. Because it's not, you have no information from the past.
Absolutely. I mean, first of all, there are two principal ways of addressing these sort of structural breaks or changes. One, you can try to do that by scenarios. Yeah? So you exogenously have a story of how things change, and then you make your model comply to that. Yeah? That's sort of, I would say, the easy one and most often used one, especially for the large-scale simulation models I talked about, that are very rigid in structure. Yeah? So there is a certain supply behavior, and that might change the parameters, but the principle stays the same. So the other way is going into the agent-based models and sort of going down to smaller processes. Yeah? If we go down to modeling smaller processes, then the structure can change also potentially endogenously. So then you implement or you adopt the technology, and then certain things happen, and the structure of the system changes because we have a dynamic interactive system. So some of these things that the old traditional models cannot do, in principle, these agent-based models can, and they are more geared towards transformative change. But there will always be some things, you know, where you have structures in the model that are there, and they are presupposed, and where you have limits, and then you need to deal with scenarios if you think that's a limitation.
Okay, but what do you think from your experience? Is this assumption we will have these small, tiny machines? Is it something like disruptive, or is it only a small part in the whole system? And let's say, okay, it's another technological developments as we had in the past since decades. Yeah.
So I think one of the disruptive elements that we thought of think about is that perhaps, as we can see already with some services offered, that the whole crop management is outsourced. So if it's really high-level technology, requires certain skills or very expensive machines, then it might not be done so much anymore, certain aspects of it on farm. So that would be more than a marginal change. It would also change sort of the skill levels required on farm to operate a farm. So the one other thing, therefore, we look at the labor market implications. My feeling, I mean, that's why I'm in this project. I think it will be a disruptive or major change, but it will not happen as a shock and suddenly come. It will be, nevertheless, a continuous development, but it will be a substantial development, a major one happening over a few years. But it will not be a shock like an extreme weather that destroys a resource base or something.
So it might happen that the farmer himself or herself is not carrying out the management of the field anymore.
Yeah, which already starts to happen in some context, depending on what are the household structure, but also what are the types of crops they do. We have the firms already offering for 100 euros a hectare management of certain crops. So I think it's going potentially in that direction. And it depends on the size of the machines and for what purposes they are used. Yeah? If it's more an investment done on farm, where also the skills can be used that are available, and where control and not having to wait for others and things like that matter. Okay. But it could be other technologies where outsourcing is.
It's not easy to predict. At least for us, it's not easy to predict.
No. Well, for us not either, but I know this is one of the key things that we want to look at.
How can we test these models? I mean, now specifically for PhenoRob, will we be looking in the region here and pick out farms and then see how we can test these models? And
well, you can.
Is it more an academic way of looking at controls as possible? I don't know.
Well, good point. So we cannot do the experiments that natural scientists do to sort of test whether the model works, at least in most cases. Yeah, we can sort of empirically validate subparts of the model, but that is limited with respect to the overall. So what is typical for these larger scale simulation models, to see them as a laboratory, so a way of consistently combining assumptions. Yeah? And then seeing what happens, because you cannot do that analytically anymore or talk in a story through that. So that's one part. And then You can try to assess also with some past data, do they generate the same dynamic or spatial patterns that we observe in reality? So there are some techniques of validation, yeah? Do they in principle capture the most important processes? But it will always be limited.
What would be a convincing argument for a farmer to adapt the technology that we will develop in PhenoRob? He wants to have a benefit. Benefit is the driver. So, yeah. And I don't have any feeling how much a farm or farmers have here capital to invest in such a technology that will give them a return on invest. And I don't know, I don't have any feeling for that. We might be working on a technology that is scientifically great, gives us a great deal of pleasure in doing all that research. And then, if you then go to the market, and then you will say, well, tell us, if we implement this technology, will I have a 5% gain? Will I have a 10%? What will be the benefit? And I don't have a feeling for that.
Yeah.
Is that something
Well,
that
that's exactly why I think we are in this project, because we want to deal with that. But it's not sort of profitability. So what maybe came out through some of the things I talked about is that it's not only looking at the single technology. You cannot say this technology will give you a 5% gain and therefore they adopt it. So it might depend on, that is an average consideration. Yeah? What is the average increase in profitability? But what happens to risk? Yeah? Is the variability going down maybe of yields between years, or is it increasing? Does the farmer have control over the management decisions? Do they know what is actually done by the machine? Yeah? So this could be a factor that makes them adopt it or not. So their own ability to control the process still, based on their experience. There will be things we look at, has the neighbor successfully implemented it and is happy about it? That will obviously make a big difference in terms of the adoption in space. How are the extension agents working with these technologies and so on? So there are all kinds of people involved. So it's not going to be sort of the accounting part. It's also important, obviously, at the end whether there's profit coming out, but it's the interplay.
My question is more, is it an on-top investment that he needs to do because he still has his tractor, he still has his costs and so on, and then you say, now but we have the robots here, so you have your tractor, you still have to do all the work with the tractor, and then I don't see, well, I've been thinking about it, will it be a farm without a tractor and only robots? I don't think he will say, I don't need a tractor, so he will still need his tractor.
But this
and then the question is, where is our technology coming into play in that system? That's what
but this is exactly what I meant with technology attributes and the whole system, yeah? So we need to understand, what does it replace? What is the substitution that's happening? And not only what it does, and does it give a good yield or a stable yield or a good ecological impact. So we need to understand how, relative to the current situation, the system is changing.
Comment on this and then one general observation. So in one of the CP meetings, I think it was Sven Winke who gave a nice example of a robotics application that would replace something very costly in agriculture. It was in asparagus harvesting. Yeah, so we know, and it has been in the news, this is a very labor-intensive activity. Farmers in the region have difficulties in finding workers for that, and that's something that, and the robotics experts can judge that better, but that would seem like an activity that robots could do. Yeah? So it could replace this very expensive or increasingly expensive labor activity, and that would be an additional incentive for a farmer to say, hey, I don't need, it's a service, I contract this as a service. Of course, for a farmer to afford one robot to do this 3 months in a year is not worth it, but if you have 20 or 100 farmers, and the robot could do it night and day, basically, then you have disruptive change in such a system. But I think, and that's another observation I had when sitting through these CP meetings, we should not only wait for us to see robots doing all these things, because what I found in most of these CP meetings, you guys will be using sensor techniques and information gathered to improve knowledge about what might happen in terms of what will the yield effect of what's happening now using machine learning. So we will improve the information ultimately with the goal of informing a robot decision, but it could also inform a farmer's decision now, right? So maybe we take out some risk out of the cropping system with what we do in these core projects. And that's something that these models can also do very nicely. They can tell you how will the decision of farmers change if you take out risk. Will they apply more fertilizer? Will they invest more labor in doing one or the other activity? Just because they know with more certainty that in 3 or 4 months I have a higher yield, or I have a lower disease incidence and things like that. And so maybe this we need this as a plan B, because these robots will not come about in the next year.
Well, actually, this was along with Harry's question of how much time do you spend actually in your efforts in developing these models, but how much time do you spend in validating these models? And you mentioned this one example where they were like showing that the policies to mitigate climate change actually have a necessary effect. They actually increase food shortage. How much can it be validated, and how much do you in particular spend in this?
That's a good point. I would say they are not validated enough. And typically in these ex-ante evaluations, you will not, as an analyst, live when the outcomes actually show. Yeah? And so these, especially in the context of climate change, the simulations are 2050, 2070, so many years from now. Again, it can only be validated with respect to, do they simulate the assumptions you made correctly? Yeah.
But if you take away climate change, go back in something else where you have data from 20 years ago, and then you say, no, you got it 20 years ago, and you find out that you actually are able to know what happens now. Then you see how good your model is. Is that a possibility?
That is a possibility. It is also done, sort of these backcasting and things, but it's for this large-scale model a major effort, and you need to get funding for that. And the people, the donors, typically only want to look forward. Yeah, but no, but there's this sort of a discussion in the community of integrated assessment modeling for a long, long time, and there are all kinds of ways out. So you use now multi-models, yeah, as in this nature study. Yeah, so there were 8 models involved, and if they all go in principle with respect to the message in the same direction, then there must be something right. Yeah, so that's how they work. Or they call it an extended peer review process. Yeah, so I mean, Capri is continued to be used because it has now, in the eyes of those using it, developed useful information for many years. Yeah, and then it's sort of self-supporting. Yeah? So they call it extended peer review, yeah, by the use of the model. So, but you can see I'm stumbling here a little bit, because that is definitely an ongoing and always existing challenge in that modeling community.
And that's probably a question you get often, right?
Yeah, sure. I'm used to that.
Yeah, thank you, Thomas, for the interesting talk. I have a question concerning the title. So coming back to what you said towards the end, that you want to generate knowledge on the determinants of the adoption of PhenoRob technologies, whereas in the title you're actually going beyond that in the sense that you were saying you do this for influencing the policy discourse, right? So I wanted to ask you whether you already have a strategy for how you're going to influence this discourse. Like, do you, or I mean, beyond what you said towards the end when you said you want to link the outcome of the different CPs, which is essentially, I think, the first step in influencing this discourse, right?
Mm.
But then, how do you want to proceed from there? Do you have something?
No, to be just clear. I mean, for me, the sort of issue of policy and how sort of institutional government might now in some way sort of affect the system, I always thought about this at the second phase of PhenoRob at the end. But I know, in principle, maybe we have to think about that earlier in some respect, but in principle, for now, it's understanding the processes. Yeah? And our models are made ultimately for then injecting a policy shock at some way, yeah? Changing the profitabilities, setting up an extension system or this sort of thing. So it could be simulated, yeah? What would that change in terms of the system, or subsidies for environmental beneficial outcomes, yeah, that then may benefit these technologies that, as we hope, have also a good impact on that side. Yeah. So, but this is sort of more the bread and butter of economists, which ultimately, when we have a running model, can always insert, yeah, what is then current and topical in the policy discussions on that. But now we need to understand how the system works first.
I guess finally, at least for me, you need to pick a case study or something, right? And we've had a really interesting discussion here about European farms, horticulture, Africa. Will you pick a scenario? And what would that be?
We have not really explicitly made that decision, but we always implicitly thought that because everybody's working here in the German environment, and with the experimental fields here and the biophysical conditions and so on, that we at least start with the core modeling activity, putting it in this context. Yeah?
Well, there are several German scenarios,
Mm-hmm.
like there's potentially broadacre. I would say a big important thing to look at would be the difference between broadacre, so something like wheat or barley, or versus horticulture, very high input, very valuable. Would we even decide between those two systems?
Well, for me, I have only a limited overview on what is currently discussed, but when I was in CP4 and the use cases there, yeah, with fertilization and weeding on the crops of barley, sugar beet, and what was the other one? Maize. So that really made me think that this area here, for example, in North Rhine-Westphalia, and then looking at the farm population as a whole. Yeah, we don't decide to look only at a certain type of farms, because our understanding is that the sector is in a lot of ways connected, and you typically lose a lot by only focusing on certain types of farms. Especially when you go into the regional upscaling, you cannot forget the animal production systems, even when you only look at crop management. So I think our choice would be to give it an empirical context like North Rhine-Westphalia. Yeah, that would probably be, for all kinds of reasons, a good starting point. And then we have sort of more limited scoping studies and papers thinking about the broader European global possibilities of such technologies. But yeah, this is still open.
Okay, last question.
I have problems to understand what are the actual parameters that you estimate in models. So especially if you have livestock, household, and land use, which for me sounds abstract somehow. So,
Okay.
So and then you had this nice plot where you had a vector, a mathematical vector. So what are the actual components of the state vector in the model? Like an example.
I mean this one, no?
Yes, for example, what are the very concrete, what is this number, for example? And what are numbers or variables that you could use to feed into the model, which you could potentially get from other core projects?
So it could be, for example, the expected yield of wheat, yeah, under the biophysical condition, the soil fertility of that farm, and so on. So there could be,
farm, for
Of one farm, yeah. But for next farm it's different, yeah, because the resources, the soil fertility changes. Could also be distinguished by the plots. So that you actually have heterogeneity and differentiation across the plots. So and then the interplay between expected yields and the variability of yields, which I can express by standard deviation or kilogram per hectare, whatever, tons per hectare. These sort of things go in and then are chosen, or among the alternatives of land management, then our model chooses, depending on all these parameters.
Is information from Frank's model or from Harry's, is it right?
Maybe at some point, yes, for example. I mean, when we go back to this, we already did, yeah? I mean, let me point out that this here, what you refer to, is actually a study that was done in collaboration with Frank's group, where the vegetation, the rangeland model, was done by a PhD student of him. So this model then generates really what is the feed quantity that is available at a certain point in time. What is the quality of that? So that is then translated in the model into growth rates. But also then the grazing that is done on the field is going back into the rangeland model and changing there the conditions, because grazing affects the vegetation dynamics and so on. So it's very concrete. There are concrete numbers. I stayed at the conceptual level, that's true.
Yeah.
So the last question, when you think about the technological development in PhenoRob, so using robot, this autonomous multi-temporal thing, and on the other side with the farmers, on a different budget scale, what we can expect that farmers on the different budget scale will invest time, money to learn and to buy technology, or we can expect some side business, other business, technological business, which can provide the service to the different, again, budget.
Exactly.
So is it something, some
Well,
will invest, more of them will use some services, so we can expect increase of the other technology business and service?
This is sort of a hypothesis of us. When the technologies involve large investments, then it will rather be services that provide that.
Is it payable to all the farmers?
Are you asking me that, or whether I know the answer already? That's exactly what our research is. Payable, yeah? Do they want it? Yeah? Does it give sufficient benefit for their operation to do it? And this depends on the multitude of factors. Whether they have credit, that's, whether they get the money from the bank, that's probably one of the least problematic ones. If it's really profitable, they will get money from the bank. But what's more important is it not more profitable to actually share a machine among many and make it cheaper to get the same technology than have it on farm?
Some social component.
Exactly. So that's what we deal with, or we try to deal with in our modeling.
Okay. Thanks a lot to everybody.
Thank you.